Welcome, everyone. For today's prep, we're going to start to look at the second derivative test, and we're going to see how we can use the second derivative to help us classify the critical numbers for a function. So, let's get to the main result. And the second derivative test here says that if we have a critical number x equals c, so x equals c is going to be our critical number, and it's a special critical number. This is one of those critical numbers where the derivative is equal to 0. So we know for a critical number, there's kind of one of two things has to happen. Either the derivative is equal to 0 there, or the derivative is undefined there. So we're only going to be considering the cases when it's a critical number where the derivative is 0. Okay, so we have this critical number, and it's probably the more common of the two. Most of the functions we looked at critical numbers where the derivative was equal to 0. There are a few cases where we had some undefined ones, but most of the ones we've seen is where the derivative is equal to 0. Okay, so what does the test actually say? So we're going to calculate our second derivative, and we're going to plug that critical number into our second derivative, and we're going to see what we get out. And we're just going to keep track of whether the value is positive or negative. So if we get a negative value, so it's less than 0, then our function has a local max at the critical point. And if we plug into the second derivative and we get a positive value, then our function has a local min. And if we plug into the second derivative and we get 0, well, then this test is inconclusive, meaning it doesn't work. So instead, what we would have to do is use our first derivative test. So we might see an example where this happens. It doesn't happen too much, but sometimes it does happen. So if the second derivative test is inconclusive, we always have the backup, the first derivative test. And the first derivative test always gives us a result. So that's kind of a nice thing. All right, so let's kind of think of a way to remember what this test says. And we want to think of it in terms of concavity. So let's suppose that we calculate f double prime, we plug in our critical number, and we find that this is positive. Well, what does positive mean if we think in terms of whenever we're using the second derivative? Remember, we use the second derivative for intervals of concavity. So when the second derivative is positive, that means concave up. That means our function f is going to be concave up. So to kind of remember this test, let's draw what the concave up looks like. It looks something like this. And so when we draw the concave up shape, not only does it look like this is going to be a low point on our graph, but that's precisely what this test says. When f double prime is positive, we have a local min. And if we play the same game, we take the critical number, plug it into our second derivative, and we get a negative. Well, what does that mean if we think of, again, second derivative, we want to think concavity. So what does that mean for concavity? Well, it means concave down. So a way to remember, draw the concave down shape. That's what concave down looks like. And when you draw the shape, it looks like we're going to have a max, and that's precisely what the test says. We have a local maximum. All right. So I recommend when you do these, draw the graph, draw the concavity as a way to help remember, because this test it's kind of counterintuitive. When you calculate the second derivative and you get a negative, you would almost expect a negative. You think negative, you're going to think minimum. And it's kind of the opposite. If we calculate the second derivative, we get negative, it's actually going to be a maximum. So it's kind of the opposite of what you'd expect. Same thing, if we calculate the second derivative and we get a positive, well, positive, you think that's a good thing. You think you're going to have a max. Well, no, it's kind of the opposite. You actually have a minimum. So it helps to draw the shape of the graph to kind of help remind you, what does the shape actually look like? So let's try one example. We're going to look at example 1, just to get a little feel for how this test works. So let's suppose we've gone through all the regular motions and we've found where our function f has critical numbers. So let's say we've calculated our first derivative, set our first derivative equal to 0, and solve for x. And we found these two critical numbers, x equals 1 and x equals -2. And then we've gone further and we've actually calculated the second derivative. So we have f double prime here. And we're going to use the second derivative to help classify our critical number. So the second derivative is 4x cubed minus 15x squared plus 2x plus 21. Now, normally, we're kind of given more information here. In some of the other examples, we'll actually have to find these critical numbers, and then we'll actually have to calculate the second derivative. But we're kind of given some info here. We're just to see how the test works. So what we're going to do, let's start with x equals 1. So that's our one critical number, and we're going to plug this into our second derivative. So we're going to plug this into f double prime. So we're going to evaluate f double prime at x equals 1. So in the function here, wherever you see an x, change it to a 1. So when we do that, we get 4, and 1 cubed is just 1. Then we get minus 15 times 1 squared, so just minus 15. Then we get plus 2 times 1, so just plus 2, and then plus 21. And if we simplify this, what do we get? Well, 4 minus 15 is negative 11. And then we've got plus 23 over here. So we've got negative 11 plus 23, which is equal to positive 12. So we don't really care about the number part of this. We just care, is it positive or negative? So this is positive. And again, think, what does that mean? Concave up or concave down? Positive means concave up. So draw the concave up shape. There it is. And when you draw the shape, it looks like the graph is going to have a low point. So we have a local max. Nope. Local min at x equals 1. Okay, so we classified the one critical number. So we know we have a local min there. Well, now let's try the other one. So we got x equals -2. And we're going to plug that into our second derivative. So what do we get? Well, we get 4 times -2 cubed. So with negatives, it doesn't hurt to actually show a little bit more of the arithmetic here. So we get 4 times -2 cubed minus 15 times -2 squared plus 2 times -2 plus 21. Okay, so let's simplify each of these. So for the -2 cubed, well, it's -2 times -2 times -2, so that's -8. And -8 times 4 is -32. Then -2 squared is positive 4, and positive 4 times -15 is -60. So things aren't looking too good yet. Looks like it's going to be negative. And then we've got 2 times -2, so another -4. And then plus 21. And already you can tell this thing's going to be negative. This value is going to be negative. So if we want to try to simplify this, I mean, maybe it's not too bad. We can do that. What? 21 plus -32, that's going to be -11. And so we have -11 minus 60, so -71, and then -4, -75. So again, we don't really care too much about the number. It just, is it positive or negative? So we can tell it's negative here. And negative, tell what that means in terms of concavity. So negative means concave down. Draw the concave down shape, just to kind of help remember what the test says. And when you do this, when you draw that concave down shape, well, it looks like we have a max, and we do. So imagine little person standing up there, and it's downhill in both directions. So we have a local max at this other critical number. Okay. So, second derivative test is nice. It's nice because it's quick. We don't have to do sign charts to kind of figure out, are we switching from increasing to decreasing and then, or decreasing to increasing. It's just figure out the critical numbers, then calculate the second derivative and plug in. Kind of all easy things to do. The one downside to the second derivative test, so this one tends to be quicker than the first derivative test. So when we get to a lot of the application sections, this will probably be our go-to test. The one downside, though, is sometimes it just doesn't work. So if we calculate the second derivative and we get 0, the test is inconclusive, and then we have to go to our first derivative test. So first derivative test is nice because it always works. Second derivative test is nice because it's usually quicker. All right, so we'll practice more of these in class. So I'll see you then. Bye-bye.